All right. All right. Hello, everyone. Today we saw me LeetCode 239 sliding window maximum. So this is a hard problem. So if you are more beginner or intermediate and you haven't done many hard problems, don't feel discouraged if this doesn't make sense the first time around. Sometimes you got to watch the video again, or you have to ask a friend, or you could even ask some questions down below in the comments. I'll make sure to respond to all of them. And let's actually get into it. I'll try to explain this question in the most clear and concise way I can. So, all right, so let's read the question. All right, you're given an array of integers nums, and there's a sliding window of size k, which is moving from the very left of the array to the very right. You can see the k numbers in the window. Each time the sliding window moves right by one position, return the max sliding window. As you can see, the window size is of 3k, and we look at the first three elements. We say, hey, what's the maximum inside this array? It's 3, so we append 3. It moves over 1 to the right. 3 is still the maximum. So on and so forth. We've introduced 5 into our window. 5 is now the maximum. 5 is still the maximum. And see, we slid over to the second to last indice, which has a value of 6. And that is the new maximum because it's greater than 5. And lastly, we have a 7, which is the last maximum. All right, so I want to quickly go over what is the most brute force solution to a question like this. Well, first, what we could do is get the array and slice every window. So something like this, you slice this window here, and we have 3 slices. And then what we do with those slices is iterate over all of them and find the maximum and just append that to res, right? But what's the issue with that? Well, slicing an array takes big O of n time. Finding the maximum takes big O of n time. So that's big O of n squared right there. And we have to do that the number of windows because we have to slice and iterate through every single window. So times the number of windows. So that's big O of n squared times the number of windows. That's very inefficient and will time out. So I wouldn't even suggest trying it. I've tried it before. It didn't work. So let's get into a better solution. And what we're going to do is have a queue, and its queue is going to be monotonic. So meaning that it's only storing integers that are either increasing or decreasing. In this case, we will have a decreasing monotonic queue. So we have numbers that are bigger in the front and smaller in the back. And what we're going to do here is not append the values of nums, but the indices of nums. And why do we do that? We want to know what position each element is inside of our queue. Why? Because we need to know when elements come into the window and when elements exit the window, so we can compute the maximum efficiently. All right, so I like to firstly start off with, I quickly wrote up the indices here so we know exactly what indice corresponds to what value. And we're going to draw our queue. And remember, when I'm going through the queue, I'm going to be referring to the indices, so you can look up and just see what value they correspond to. So our queue has a couple of rules. I quickly wrote them up here, and we're going to get into how to code them and why they make sense later. But what I want to do is quickly explain the problem at a high level, because I believe that's the best way to understand these type of problems in the beginning, and then we can get into the nitty-gritty later. All right, so only elements in the window are allowed in the queue, so that makes sense. Our queue is only going to have indices of elements that are inside the current queue, or the current window in our queue. The biggest element will always be in the front of the queue, so we want to ensure that it's monotonic, so the biggest element's in the front, smallest in the back. And only append to res if we've processed at least k elements, just meaning that we need to look at the full window before we can append a maximum, because you need to check all the elements. All right, so we're going to go through and we're going to append the first indice. So let's say we're iterating through nums, and first we start off at 0. So we have a 0. We say, hey man, is this element in our queue or in our window? Let's quickly draw out the window so we can visualize what the size of our window is, because this is of size 3. So starting from the first indice down to the second indice, or the 0 index to the second index. And first we say, hey, is this element inside of our window? 0 is in the window, so that checks off. The biggest element is always in the front of the queue. Well, it's our only element, so it is the biggest. And only append to res if we have processed at least k elements. We haven't even checked the rest of the window, so we can't append to res yet. So we're going to go through and iterate again. Now we're at index 1. We say, hey, is index 1 inside of the current window? It is. Index 1 is inside the window. The biggest element is always in the front of the queue. Let's check the front of the queue. Say, hey, index 0, which corresponds to 1, is that less than or greater than our current element, which is 3? 3 is greater than 1, therefore we should pop off the first element inside of our queue. And we do that because, let's say we're iterating through this window here, the first window. If we come across a 1, and that's our current maximum, if we see a 3, what do we know? We know that 1 can no longer be in contention to be a maximum at any point because we're only storing values that are inside the window and we just found something bigger. So index 0 with a value of 1 is now useless to us, so that's why we pop it off because we don't need that element. It can never be the maximum. Next, what we're going to do is append the current value onto our q. So we're at index 1, so we're going to append that on. Now we have index 1. Next, what we're going to do is say, hey, can we append to res? Well, we've only looked at index 1. We haven't looked at 2 yet, so we haven't processed k elements, so we can't do that. We're going to iterate again. Now we're here at index 2. We say, hey, is 2 inside the window? It is. The biggest element is always in the front of our queue. So we say, hey, what's index 2 represent? -1. -1 is not greater than what's in the back of the queue. -1 is less than 3. So what does that tell us? That means that this could be a possible maximum. We don't have to pop off anything because let's say, a quick example here. Let's say the sliding window moves and 3 has been pushed out of the window, so it's no longer the maximum, and we're somewhere here. We don't know if -1 at index 2 could be a maximum, so that's why we keep it on there until further notice. We don't know. It could be the maximum in the future. We don't know, but we have to keep it on there and check. So we're going to append 2, which corresponds to -1. Now here, we say we only append if we've processed k elements. So we say, hey, have we processed at least k elements? We're at index 2, and the sliding window size is 3. Arrays are 0 index, so we have at least k elements. This is 3. So we say, let's append q at the first indice. So the first indice is what? 1. We say, what does 1 represent in our nums array? 3. So we're going to append 3 onto our res. See how that works out? If we make sure that the first element in our queue is always the largest, we can just append that onto res at the end. All right, so let's iterate again. And now we're at, let me quickly erase this. Now we're at index 3 with a value of -3. Now, here's the interesting part. Our window, as you can see, our window has now shifted. So let's draw a new line for our new window. We're going to draw this one in green. Well, we're going to draw a new line for our window. So in blue, let's do it in blue. So this is our new window size because we're currently at index 3. And we have to go back k elements, so 1, 2, and this is the 3 elements that are inside the current window. We say, hey, is the oldest element in our queue still inside of our window? Well, let's look. The oldest element would be the lowest indice. So we say, hey, we look at this 1, and we say, hey, man, are you still inside of our queue of our window? 1 is still inside of this window. So we keep it on there. Next, we say the biggest element is always in the front of the queue. 3 is still the biggest number, so we keep it on there. And we say, and this number, -3, is not bigger than the biggest element in our queue, so we just append it on because it could be a future maximum. We don't know. So we append 3. Now, we know we've processed at least k elements, so now all we have to do is look at the first element inside of our queue, which is always going to be the biggest, and we're going to append that to res. So we look, it's 1. What does 1 correspond to in the array? 3. So we append 3 on. Next, we're at 4 here. So our window has now shifted yet again, and this brown line is now our current window. Now what we're going to say here is, hey, is the oldest element in our queue within the current window? If we're looking at this yellow or this brown line here, and we see the oldest element is 1, 1 was in the previous window, but is not in our current window. So that tells us that it's essentially useless to us because it can't be a maximum because the window only goes forward. It never comes back. So that's long gone in the past. So what do? We pop it off. Perfect. So now we know. Now we look at this element 2. 2 is inside the window, so we have only elements that are inside of our current window in our queue. Next, we say the biggest element is always in the front of the queue. So this is where it gets interesting. Index 4 has a corresponding value of 5. 5 is larger than, let's look at the back of our queue, 3, which corresponds to -3. So that means that if all these elements are inside the window, and -3 is smaller than the current value we're looking at, that means we can pop it off. This can't be the maximum. Now, let's look at the next value, 2. 2 corresponds to -1. 5 is still greater than -1, so we pop that off. And what do we do here? We're going to append 4. And we say, we look through, and we say we've processed at least k elements, and we say, oh, look at the front of our queue, which only has one element, 4. What does 4 correspond to? The value 5. And what do we do here? We just append the 5 to our res. And this is the exact output as the answer, so 335. And that's how you solve a problem like this. So I'm going to quickly go into actually the technicals of how to solve this. The first thing I like to do is just create a res variable, just an empty array. Next, what we want to do is make our q. So I like to call it just q. So q equals deque, something like this. And next, all we have to do is iterate over nums. So for I in range nums, in range length of nums. And remember our rules. Only elements in the window are allowed in the queue. So how do we check that? So we're going to say while q. So while q has elements, because we have to make sure it at least has some elements in it, and q index 0. And why do we do that? Index 0, the front of our queue, will have the oldest element, correct? So as you remember when we popped off index 0 or index 1 because it was no longer inside of the window? So we want to look at the oldest elements first. So we say, is q at 0, which is the oldest element, is it, if it's less than the current index minus k minus 1? And I'm going to quickly explain why this works here. And what we're going to do is, let me quickly go back here. What we're going to do is pop q.popleft. All right. So as you remember here, let's pretend that we're looking at this window, the brown window. And let's say we had the indice 1 inside the front of our queue. Let's just pretend there was a 1 there. We know that that's outside the window. So how do we check that? We have to look at the current index we're in. So the index that was currently outside of our window. So let's say we had the 1. We say, hey, 1, is it less than the current index we're at? So let's say we're at 4. 4 minus the window size. So 4 minus k minus 1. And we do k minus 1 because the window size is not 0 index. So we have to make sure it's 0 index by subtracting 1. So what's k minus 1? 3 minus 1 is what? 2. 4 minus 2 is 2. 1 is less than 2. Because what does 2 represent? 2 represents the smallest index that could be inside the window, right? So 2 is the cutoff point here. If you're anything less than 2, then that means you're no longer in the window and we have to pop you off. So if we're looking at this either index 0 or index 1, those have to be popped off. So that's why we pop left. So this ensures that elements that are inside our window are inside of our queue. And we pop off elements that fall outside of the queue, right? Next, what's our second rule? We need to make sure the first element is always the biggest. So what we do here is say while q and q at -1. We're going to check the back of the queue because as you remember, the back of the queue is the most recent element that we added, right? And if we find an element that is bigger, we need to pop it off because that can no longer be the maximum. So while q at -1, that's an indice. So we're going to say nums at q of -1 is less than nums of I. So if our current value we're looking at is greater than the thing in the back of the queue, we need to pop it off because that can't be the maximum anymore. So we're going to say q.pop. And we're popping because we're taking elements from the back of the queue. Because remember, the back of the queue is the most recent elements added, and elements in the front of the queue are the oldest elements added. Perfect. Next, what we want to do is say, we check that, so now we want to append our variable. So we're going to say q.append I. And here, what we want to do now is, what's our last rule? Only append a res if we've processed at least k elements. So how do we know that? We're going to say if, so what's our last rule? We say only append to res if we've processed at least k elements. So how do we do that? We just need a simple if condition. We say if if I, which is the current index we're on, minus k minus 1, which is the window size, minus k minus 1, is greater than or equal to 0. We're going to say res.append q, which is the biggest element, and we want to make sure that that's an indice, so we want to make sure to get the actual number. And why do we do this? We need to make sure we've at least processed k elements. And how do we know that? Let's say we're in this array. Let's just say we have an array here of 1, 2, 3, and we're at index 1, and the k is 3, right? We know that we haven't processed k elements because look, the first element, the index we're on is 1, minus the window size, so k minus 1. K minus 1 is 2. 1 minus 2 is -1. That means the window has to go from here to index -1. There is no index -1, so that means we haven't processed at least k elements, so we should not append to res. So this just checks that we've at least processed k elements. And lastly, what we want to do is return res. And let's quickly see if this works. Return is outside. Okay, a quickly indent error. Let me quickly tab that in. Let's try one more time. All right, there we go. And we solved the question. And it's actually relatively efficient. So if you learn something new or have any questions, please comment them down below.